Hello everyone, I'm Bruce Lee. This is our final presentation. And I will be introducing transient heat transport problem involving phase change. Commonly referred to as phase change or moving boundary problem. Firstly, this problem is very important in many engineering applications because the interface between the solid and liquid phase is moving as the latent heat is absorbed or released at the interface. Next, I will introduce mathematical formulation of phase change problem and stated diffusion equation. One is solid phase temperature, another is liquid phase temperature, and the interface energy balance at S of T is improved heat flux conduction from the liquid phase plus rate of heat liberation during solidification equal heat flux into the solid phase. And assuming density, liquid and solid are equal, and the interface condition is simplified to this equation. And this problem we have three unknown to solve. This temperature for solid phase and temperature for liquid phase. Another is the location of the solid to liquid interface. And next, at the solid to liquid interface, the temperature must remain continuity in this sentence. And summary, equation 12-1a, 12-1b, and 12-1c provide three differential equations that differ the temperature distribution in the solid and liquid phase and the station S of T of the solid to liquid interface. And equation 12-3 provide two boundary conditions.
This part I will introduce the melting problem, and these two equations is governing differential equations, and this one is for liquid phase, and the range is from 0 to S of T, and this one is solid phase, and the range is from S of T to infinity. In the figure B, the position S of T represents the interface between the solid and the liquid phase, and energy balance as S equal S of T, and the equation is conduction heat flux from the liquid phase in the positive X direction, negative conduction heat flux into the solid phase in the positive X direction, equal rate of heat absorbed during melting per unit area of interface, which yields is this equation. Rearrangement the above equations to this one. So appropriate boundary and initial condition need to be specified for their solution. Velocity of the interface in the positive X direction is these equations. Then the interface energy balance equation can be written as this one. And this one is effects of density change. To illustrate the effects of density change, consider the one-dimensional solidification problem illustrated in figure 12. In physical situation, the interface velocity is in the positive X direction, and that solid density bigger liquid density. So the motion of the liquid is in the proper opposite direction. Energy balance as the interface, the diffusion and the convective energy transfer equation is this one. And this one is conductive heat flux in the solid phase, and this one is conductive heat flux in the liquid phase, and this one is convective energy transfer due to density and enthalpy difference, and this one is energy correction caused by the liquid flow. Next conservation equation is this one, and we can be rearranged to these equations, and we can obtain these equations. These equations, the interface energy balance is simplified to depend only on the interface velocity and the latent heat. And this part is effects of convection, solidification problem in figure 12.1. If the heat transfer from the liquid phase to solid liquid interface is controlled by convection, and therefore diffusion in the liquid phase is neglected, and the equation is this one. And these two equation difference is this is negative, this is plus, and this is solidification, this is melting. And I will explain the negative and plus difference. In the solidification, heat flows out of the liquid phase, making the convection turn negative. In the melting, heat flows into the liquid phase, making the convection turn positive.
Okay, next I will introduce nonlinear method of interface condition. Using equation 12-3, we can get this formula. And divided by dt, we can get 12-14b, and which can be rewritten. We can get these two formulas. These two formulas into equation 12-2c. We can return 12-15. Okay, that's it. Okay, next I will introduce generalization to multi-dimension. Yes. Okay, so similar to the Pareto method, the difference is that Pareto provide another form of the equation. Yes, 12-19. So from the 2D problem, f of x dt equal to z minus s of x t. So we can get equation 12-20. And for the one-dimension problem, we let f of x dt equal to z minus s of x equal to 0. So we can get 12-21. Okay.
Hello, and here's my part for the example 12-3. And this is a problem with a solidification problem, and we have two phases, and one is solid and one is liquid. And so we have to write a heat equation first. Because we have two different phases, so we have to write two different heat equations, separated to the solid phase and the liquid phase. So the first two equation is for solid phase, and the second question is for the liquid phase. And we have to notice that the initial temperature of the liquid phase. Yeah, because we see the diagram, and maybe we will write Tn to the initial temperature for liquid phase, but we have to see the question, and the question says the initial temperature is for Ti. And after we wrote these two equations, we have to write the complete conditions because we know we are at same points in the solid phase and liquid phase. So we can use the diagram to write the equation 12-47. Yeah. And so due to our previous learning, we can write the solution to the temperature for solid phase and liquid phase. So it is the solution with the error function and complementary error function. And then from the coupling condition, we can write down the equation 12-58. And then we have the coefficient A and B. So we have tried to perform these two coefficients. And so we define other eigenvalue like 12-50b. And then substitute to 12-58, and then just move on the part, and then just to perform A and B. So we can write down A and B just like 12-51. Okay, and then we just introduce the coefficient A and B, and then we can just put back to the previous equation, and then we can get equation 12-52a and 12-52b. This is the equation from the temperature from solid phase and the liquid phase. And then we can just put back to the previous equation like 12-47b. And then we can use to determine the relation for the evaluation of the parameter eigenvalue, lambda. And then we can just put to the previous equation like 12-50b, 12-52a, and 12-52b. And then we can just get the final equation, 12-53. And we can know if this lambda we know, and then all the like temperature in solid phase and liquid phase, or the function of the all temperature can all be determined. So this is for example 12-3. So this is final presentation for group 3. Thank you for listening.